Equilibrium computation for two-player games in strategic and extensive form. We explain the algorithms for computing Nash equilibrium of two-player games given in strategic form or extensive form. The strategic form is a table that lists the players' strategies and the resulting payoffs. The best response condition states that in equilibrium, all pure strategies in the support of a mixed strategy must get maximal and hence equal payoff. The resulting equations and inequalities define the polytopes whose completely labeled vertex pairs are the Nash equilibrium of the game. The Lemke-Hossan algorithm follows a path of edges of the polytope pair that leads to one equilibrium. Extensive games are game trees with information sets that model imperfect information of the players. Strategies in an extensive game are combinations of moves, so the strategic form has exponential size. In contrast, the linear-sized sequence form of the extensive game describes sequences of moves and how to randomize between them. Introduction. A basic model in a non-cooperative game theory is the strategic form that defines a game by a set of strategies for each player and a payoff to each player for any strategy profile, which is a combination of strategies, one for each player. The central solution concept for such games is the Nash equilibrium, a strategy profile where each strategy is the best response to the fixed strategies of the other players. In general, equilibria exist only in mixed randomized strategies with probabilities that fulfill certain equations and inequalities. Solving these constraints is an algorithmic problem. Its computational complexity is discussed in Chapter 2. In this chapter, we describe the methods for finding equilibria in sufficient detail to show how they could be implemented. We restricted ourselves to games with two players. These can be studied using polyhedral because a player's expected payoffs are linear in the mixed strategy probabilities of the other player. Nash equilibria of games with more than two players involve expected payoffs that are products of the other player's probabilities. The resulting polynomial equations and inequalities require different approaches. For games in strategic form, we give the basic best response condition. Proposition 3.1, see section 3.2, explain the use of polyhedra, section 3.3, and describe the Lemke-Hossan algorithm that finds one Nash equilibria, section 3.4, and implementation without numerical errors uses integer pivoting, section 3.5. Generic games, i.e., almost all games with real payoffs are non-degenerate. See definition 3.2. Degenerate games are considered in section 3.5. An extensive game defined in section 3.7 is a fundamental model of dynamic interactions. A game tree models in detail the moves available to the players and their information over time. The nodes of the tree represent the game states. An information set is a set of states in which a player has the same moves and does not know which state he is in. A player's strategy in an extensive game specifies a move for each information set, so a player may have exponentially many strategies. This complexity can be reduced. Subgames, see section 3.8, are subtrees so that all players know they are in the subgame. Finding equilibria inductively for subgames leads to subgame perfect equilibria, but this reduces the complexity only if players are sufficiently often, e.g. always informed about the game state. The reduced strategic form applies to general games, see section 3.9, but may still be exponential. A player has perfect recall if his information sets reflect that he remembers his earlier moves. Players can then randomize locally with behavior strategies. This classic theorem, corollary 3.12, is turned into an algorithm with the sequence form, sections 3.10 and 3.11, which is a strategic description that has the same size as the game tree. We give in this chapter an exposition of the main ideas, not of all earliest or latest developments of the subject. Section 3.12 summarizes the main references. Further research is outlined in section 3.13.